Hello and welcome to our discussion on model fit assessments in our Python notebook. So today my partner and I will evaluate the best performing regressor and discuss the tools that we use to assess its fit and any improvements we made. So let's begin by identifying the best performing model. So before we dive into the specifies, let's define what we mean by model fit. So in machine learning, model fits refers to how well a model generates to the unseen data. So a well-fit model has slow training and validation errors without being overly complex or too simplistic. So in our case, we will use the multiple tools to access the model fits. And our first step was cross-validation, where we split the datasets into the multiple training and validation sets to get a more reliable performance estimate. So firstly, I will begin by installing the necessary libraries. And these libraries help to machine learning model development and featuring the processing and hyperparameter tuning. And I'll import the request packages like pandas and numpys that are used for the data manipulations and seaborn for visualizations and warning filter, warning suppress the unnecessary warnings. And I import the additional machine learning tools. The random forest regressors use a machine learning model where hot encoder helps to transform the categorical data into the numerical forms. And this process that converts the shareable Google Drive link into a direct download URL for the datasets. And additionally, I examine the data properties. This checks to ensure that the data contains the valids and unique recorders, and they help to identify the missing values. If there's any duplicate rows exist, they're removed to prevent the biased and biased model performs. So for the encoding categorical variables, so the category variables such as sex, smoker, and regions, they are mapped into the numerical values, and this will allow the machine learning models into the interprets the categorical data effectively, and this ensure that numerical features that they are standardized and categorical features are properly encoded. And for the analyzing the data fits, so based on the tools that we use, our random forest regressor showed the strong generalizing ability, and the training error and the validation error were close, which suggests it's not overfitting. And so for the actions that taken in to improve the fit, so even though our model performed well, we will still look steps into the improve its fit. Because firstly, we turn the hyperparameters using the grid search CV. We optimize the key parameters like max dip estimators and mean sample splits to balance the bias and variance. So while we processing the steps in model training were execute effectively, there are still some potential limitations that could impact the overall reliability and also the fairness of the model. So two key concerns that are data bias and also the feature importance. So if the data set has more non-smokers than smokers, the model may unpredicted medical costs for smokers. Similarly, if the certain regions dominate the data, the model might not generalize well, and mitigation strategies include the resampling techniques and stratified the sampling to balance the distribution. And another concern is about the feature importance. Not all the features contribute equally, and some may add the noise. So using the random forest feature importance scores for SHAP values that can help identify the most relevant features, and removing the low impact variables can simplify the model, while missing key factors like pre-existing medical conditions may limit the accuracy. So to improve the fairness and the robustness, strategies like better data collections, feature selections, and also fairness aware modeling should be considered and ensure aware balanced data sets and refining feature selections that will help lead to a better generalizing and interpretability.
Uh, Now we move to the next part. It's talk about the model selections. And then here we run a simple check for missing value in both training and the testing data sets to ensure there is no missing data that could disrupt the model performance. These categorical features were transformed using one-hot encoding, which converts categorical variable into a machine learning compatible. Next, we validate the data type weights, indicating that our numerical and encoded feature are properly formatted for training. We check for missing value in the training data. If there are none, we skip imputation. Otherwise, we use simple imputers to fill missing value with the column mean. Next, we train a linear regression model on the clean data. Using the training model, we predict the target variable for the test data. Finally, we confirm that the shape of X test, Y test, and the prediction, they are present matching, ensuring the pipeline runs smoothly. We start by initializing the decision tree regressor with a fixed random state for consistent results. The mean absolute error indicating average absolute difference between predict and the actual value, indicating the model's overall accuracy. The mean squared error presents the average squared difference, heavily penalizing large errors. R squared, which measure how well the model explains the variability of the target variance. Here, 79% of the variance is explained. We do compare between linear regression and random forest models. Linear regression model suggests the linear model provides reasonable accuracy but has room for improvement in capturing complex patterns. The random forest model outperforms linear regression, kept more variability in the data because the R-square presents 88.2% and producing lower errors. This comparison highlights the strength of random forest regression is handling complex nonlinear relationship, significant outperforming linear regression in both error metrics and explanatory power. This visualization compares the prediction performance of linear regression and random forest regression. The prediction of linear regression align reasonable well with the red line for lower value of charts. However, for higher charts, the prediction deviates more, showing that linear regression struggles with capturing complex relationship in the data. For the random forest model, the green points are tightly clustered around the red line, indicating that the random forest model better captures variability and relationship in the data. This model provides more accurate predictions for both lower and higher charts. Linear regression provides a straightforward approach but lacks the ability to model nonlinear regressions. Random forest regression shows superior performance as seen from the closer alignment of prediction to the actual value, especially for higher charts. Additionally, justifying trade-off between interpretable of linear regression and performance of random forest would strengthen the analysis, providing insight into models suitably for different use cases. The reason why random forest model generalize well because it combines prediction from multiple decision trees, reducing overfitting and improving robustness. By averaging diverse train output, it captures complex interaction between features while mitigating noise and variance. The last step is to import the necessary library and generate the CSV. And finally, thank you for watching and listening our video.